Now I can start or
not yet.
not yet. Okay. I can't see your face, but I suppose that it's okay.
Okay. Okay, welcome to GADEPS. Today we have Daniel Lopez who is going to talk about monodromy problem and tangential center focus problem for product of generic lines in P2. It is too long, but okay.
Yeah, sorry about that. Thank you, Hossein. Thank you for the invitation again to the seminar. Well, today I'm going to talk about my last work, monodromy problem, and this title. Well, the talk is divided in four parts. The first one is an introduction and a motivation for this problem, the monodromy problem, and so on. The second one is a description of some intersection matrix for some fibration, special fibration. And the third topic is about the monodromy problem, is a very topological part of the talk. And the last part is about this problem, tangential center focus problem, which is an application of the previous topics to, well, some holomorphic foliations. Well, let me start with the motivation of this problem, of the study of the monodromy in some fibrations. Well, the motivation coming from the 16 Hilbert problem. Here I have a weak statement of this Hilbert problem. So the idea is we consider a polynomial f, and well, this Hamiltonian foliation defined by the f. Omega is a polynomial one form defined by P and Q. And well, we consider a perturbation, a perturbation of this Hamiltonian foliation, and we have this system. And the idea or the problem is bound the number of limit cycles for this system. Let me remind that a limit cycle is a closed solution of the system, such that the holonomy is not trivial. I mean, if we consider a transversal section and we consider the first vector map, the first vector map is not the identity map. Well, we can see here, for example, that the polynomials are with complex coefficient. The original problem, the original Hilbert problem, is with real polynomials. By some approximation, some approach to this problem is, well, we can consider complex polynomials, and also we can consider this approach, which is the tangential 16 Hilbert problem. Sorry, are you listening? It's because I can't see your face.
Yeah, go ahead.
Okay, thank you. Well, we can consider this Abelian integral, which is just define the integral of omega in cycles of regular fiber of, well, fibers where this integral have sense. And the statement is, if this is not zero, is not is not equivalent to zero, then the zeros of this integral are in correspondence with the limit cycle of the previous system. So the idea of this tangential 16 Hilbert problem is bound the zeros of these Abelian integrals in terms of f, p, and q. Well, but what happens when this integral is zero? So we have to use a bigger order of approximation of this system, and so on and so on. So a natural problem here is characterize the condition under this integral is equivalent to zero along a vanishing cycle. This is the tangential center problem. And well, I want to say here that one of the most important results in this direction is given by Yuri Lyashenko. He proved that, well, he gave a description for generic polynomials f, I mean, polynomial with different critical values and critical points. Well, by using that, the main idea in the proof of Lyashenko is that, okay, if you have that this integral is zero for one vanishing cycle, then he proved that for this kind of polynomial, the monodromy action is transitive. And then if you consider the orbit of this guy, you can generate the whole homology. Then you prove that this integral is zero for any cycle in the homology of a regular fiber. Consequently, you prove that your omega is relative exact modulo this foliation, the foliation defined by f. So by using this result of, for example, Lubomir-Gavrilov, you can prove that this omega have an explicit presentation, an explicit form. So this is a motivation for this problem, the monodromy problem. Well, this was stated by Christopher Mardesic and Paul Mardesic. They consider, the problem is under which condition on a polynomial f, this space or these modules are equals. Here we have the homology of a regular fiber, and here we have a subspace of this vector space, which is, well, we consider a vanishing cycle, we consider the monodromy action acting in this vanishing cycle, and we consider the subspace generated for this one, for this orbit. And well, the problem is that characterize these orbits of the monodromy. In parallel with this history of this monodromy problem and tangential problem and so on, we have this problem, which is an open problem still, is a very important problem in foliation, in holomorphic foliation. It's a problem stated by Alcides, Linz, Neto. Is the central problem is like a, well, it's like a algebraic version of this problem. So the idea is, well, we consider the polynomials, the polynomial foliation of C2 of degree D. Here, define the degree is very easy. It's like, okay, we have, for example, a foliation defined by this omega. The degree is just the bigger degree between the polynomials. So we have the degree, the foliation of degree D. And in this space, we consider this subspace, the subspace of this subset, the subset of foliation with at least one center singularity, the closure of this one. And this, it is possible to prove that this is an algebraic subset of the foliation of degree D. So the problem is describe the irreducible components of mu D. And the main result, well, one is by Dulac for the case of D equal 2. Another one is by Lyashenko for any degree that I said before. Is he proved that the Hamiltonian foliation forms an irreducible component of mu D. Another result by Jose Movasati, he proved that the logarithmic foliation forms an irreducible component. And the last one by Jadot Lazare, he proved that the pullback foliation forms an irreducible component of mu D. And well, for example, the main strategies used here is by study the monodromy action in some particular point of these irreducible components. And for example, in the case of Hossein, he studied a foliation defined by a fibration given by a product of lines in general position. But all of these works are for foliation in C2. So the idea of this work is try to generalize the result by Hossein, but for the case of foliation in P2. So, well, this was the introduction. Now let me pass to this another part, intersection matrix. So here we have, as we say, we want to generalize for the case of projective space. So in this case, we have any more polynomial, we have to consider rational functions. For example, this f, like p over q, with point of indeterminacy, the set of p equal q equals 0. For sure, well, we can or we suppose that this indeterminacy point of indeterminacy have a codimension of dimension 1 or something like that, in order that the things are easier or better understanding. Well, for example, if we have this is the case that we have at the beginning. It's not a fibration for sure, because all the fibers intersect in the point of indeterminacy. But if we consider blow-ups over the point of indeterminacy, we have something like this picture. Then we have a fibration here. Let me set some notation. This LK is just the pre-image by F of a compact set in P1. For the theory of Lefschetz, Picard Lefschetz, we have this result that if we consider the homology of this pair, where A and B are regular values. So here we are consider the preimage of the affine, well, we consider a affine chart of P1. We avoid a regular value and we consider this preimage. And here we consider the preimage of a regular fiber. So the Picard-Lefschetz theory, by using Picard-Lefschetz theory, we can prove that this homology, relative homology is 0, and the homology to homology is a free module. Then the generators of this relative homology are the Lefschetz symbols, are called Lefschetz symbols. And we have this sequence given by this pair, this sequence in homology, where this map is the boundary map, and the image of the Lefschetz symbol, the boundary of the Lefschetz symbol are called vanishing cycles. And it is possible to also prove that this homology is 0. Then we have that this is a surjective map. Consequently, we have that the vanishing cycles generate the homology of regular fibers. It's not necessary a basis. I mean, just generate. It depends of the kernel here. Well, we have another. Well, this is like a kind of definition. We have the Dinkin diagrams, which are a form to relate vanishing cycles. A Dinkin diagram is something like that. In the vertex, we have vanishing cycle, and in the edge, we have the intersection between vanishing cycles. The idea is if we have the intersection between vanishing cycles, by using the Picard-Lefschetz formula, we have the monodromy, explicit description of the monodromy action. And a very nice result by Norbert A. Campo is if we have, for example, a polynomial with real coefficient. This is an example, a very explicit example, but we can consider any polynomial with real coefficients, or such that we can factorize this guy as product of polynomial with real coefficients. Then, if we have that, we have a graph given by the level sets of this hypersurface. Then the theorem of A. Campo is that with this graph in the plane, in R2, we can describe the Dinkin diagram. We have to look like the intersection between a vertex and a relative compact component and so on. This is maybe a classic theorem, very nice theorem. This theorem is used in the work of Hossein in order to compute the monodromy action of the product of lines and so on. And the idea is try to generalize. It's not like a complete generalization of this theorem for any rational map, but for the case that we want to study. And what is this case? This is a general proposition, and not for the case of studying this article. The proposition is the next. We have a rational map. Sorry, I want a little of water. Sorry about that. Well, we have a rational map, P over Q, and we have vanishing cycles, alpha minus and alpha plus, defined in a regular fiber. We say that these vanishing cycles vanish over respectively A plus and A minus. And well, suppose that both vanishing cycles are at real center points, or both are vanishing cycles at saddle singularities. So let me just show something. Well, this is like a center singularity in the real plane. Is a singularity such that looks like this one, and a saddle singularity is such that locally looks like this one. For sure, they are different in the real context, but for sure, by doing, for example, a transformation like this one, they are equal or equivalent in the complex context. But well, we are considered just in this part in the real plane and so on. So let me continue here. So suppose that both are over real center or both are over saddle singularities. And the theorem is, the proposition is there are not critical values in this interval, then the intersection between this vanishing cycle is equal 0. And the same is true is for any critical value between in this interval, the vanishing cycle over A0 doesn't intersect A plus. So we have an explicit description of some intersection between vanishing cycle, which will be 0. And this is the main ingredient in order to prove the first main theorem in this work. So, well, let me talk a little more about the case of the study in this article. As I said before, this is a kind of generalization of the polynomial study in the work of Hossein and other works like works of some students of Mardesic, like Mark Uribe and Jesse Pontigo. They studied this for C2 or product of lines in general position, and here we study the quotient of product of lines in general positions, D+1 lines and D+1 lines here. For example, the numerator here in the, well, this is a line in P2, but we can prove or we can show that the critical points are in the affine chart C equal 1. And well, we can also draft these lines in the real plane and so on. So, for example, P in the real plane looks like the union of these lines in green, and Q looks like the union of these lines in blue. And here we have the vanishing cycles, and we have like three kinds of vanishing cycles. This delta P and capital delta P are related with the polynomial P, and delta Q and capital delta Q are related with this polynomial Q. And let me talk about a little more about this one. This vanishing cycles here appears, for example, because we have intersection between these lines, that these are these guys, which looks like saddle points in the real plane. But also we have this in circles in green, here, for example, which looks like which are local maximum or local minimal, and they look like center points in the real context. And something, or well, we know this like this vertex in like a little delta, and the other ones like a capital delta. And well, something similar happens for Q. But also we have another vanishing cycle, which are because we have a rational map. And what is the idea? We have these points in black, which are the point of indeterminacy. Remember that P equal Q equals 0. And the foliation near of this point look like lines which going from this point to this point, and this point from this point, and so on. Consequently, in the middle of this relative compact component, we have a saddle singularity. And we denote that by sigma K. Then this is the family of vanishing cycles which are considered. For sure, we have more vanishing cycles than the dimension of the homology. Well, the first main theorem in this work is a description of the intersection between these vanishing cycles, and this gives a intersection matrix. Well, the first result coming by the theorem of Campo, and also is presented in the work of Hossein. So we have that the intersection between capital delta P and little delta P or low delta P is 1 if the point of self-intersection associated with this delta IP is a vertex of the relative compact component associated with this delta JP. Now let me come back here. For example, in this case, this relative compact component is this one, is like this triangle. These guys are vertex of this triangle. So the intersection between this guy and this guy is 1. But for example, if we have another circle here and we have another relative compact component here, the intersection between this guy and this guy is 0. Well, something similar for Q. And now the intersection between relative compact components associated with this guy and the relative compact component associated with this guy is 1 or -1, depending on the orientation. If this guy have a common edge, like, okay, we have two triangles. If these guys share a common edge, the intersection is 1 or -1, depending on well, an orientation. Something similar for Q, and it's 0 in the other cases. What is very interesting here that this guy sigma don't intersect any other vanishing cycle. And this I say that it is interesting because in contrast with a theorem of Hossein, that he said, for example, that if you have in a polynomial, in a fibration given by a polynomial, if you have a vanishing cycle and you consider the monodromy action, you can describe any cycle by monodromy action. But this is okay if you do monodromy action in any of these guys. You can they are intransitive by this monodromy action. You can move the orbit is just this guy. Okay. In this basis, for example, I just want to close this idea here. In this basis, delta P, capital delta P, delta Q, capital delta Q, and sigma K here. In this basis, we have that the intersection matrix look like this one, like this C, where CP and CQ are the intersection matrix for P and Q, and you can compute this by the theorem of A Campo, for example. But well, the intersection matrix of the rational map looks like this one. And well, this is the idea of the computation. Now let me talk about the monodromy problem, about a little more topological description of the fiber. So let me start with LB is a Riemann surface of genus. Remember that here we have, we have P and Q are product of D+1 lines. So we have that the genus of the Riemann surface is D-1/2 with D+1 to square point of indeterminacy n. So we can define this compactification, or well, compact fiber, bar LB, which is just the affine LB union with the point of indeterminacy. And if we compute the dimension, we have that the dimension of the affine fiber, of the homology of the affine fiber is this one, and the dimension of the compact fiber is this one. So if we can define I like a subspace generated by the cycles around point of the indeterminacy, then the homology of a affine fiber is just the union of the homology of a compact fiber with these guys around to the point of indeterminacy. In a picture, looks like this one. The compact homology is just these guys in yellow and these guys in green. For point of indeterminacy, this X, we have around of these guys another cycle which don't intersect any other cycle, and these are I, and the union of these cycles are the homology of the affine fiber. And well, by using the intersection matrix, the description of the intersection matrix, and well, this description, we can prove that the vanishing cycle associated with P, delta P and capital delta P, generate the homology of a compact fiber. So in this point, it's like, okay, we can forget for a moment what happened with Q and that, and just concentrate in the vanishing cycle associated with P. Here we have the second main theorem. Well, we consider this rational map, as I said before, the product of lines in general position. Then for any regular value B of F, the action of the monodromy on any vanishing cycle, so we consider one of these one, just one, also we can consider a guy for P and for Q. And if we consider this guy and we consider the orbit by monodromy action and we consider the subspace, then we prove that this is the homology of the compact fiber. Yeah, this is the second main theorem, and this is like the version of monodromy problem for this fibration. Well, now as an application, until here I just talk about like a topological concept of this fibration and so on, and now the idea is like a translate or to use these results in order to give like an application in meromorphic foliation. So let me introduce, first of all, I want to introduce what is like a Gauss-Manin connection. And for this, I need to define what is the Briscoe module and, well, or Petrov module, depending on the work. Let me define this divisor D is just the point of poles, the Q equals 0. And we know like omega I D, the set of rational I forms with pole along D. So we define the Briscoe module in this format. We consider the one forms with pole along D, modulo the derivative, the exterior derivative of rational maps with poles along D, plus df, which, well, in this case, which is just the product by some polynomial with, some rational map with pole along D. And this is the Briscoe model. And we define this B, which is the two forms with pole along D over, well, this wedge product. So it is possible to prove that this V is a vector space with finite dimension. And here we have, by consider the product by F, we define a linear map between this vector space, which we call A. Let me call PA the minimal polynomial of this linear map. Also, let me call this TC like the set of critical values of F different from infinity. So we can consider the localization of this H, or well, we can consider this H tilde, which is just elements in the Briscoe module over polynomials in the variable T, such that the set of these polynomials are critical values of F different from the infinity. How we define the Gauss-Manin connection? Well, the Gauss-Manin connection is just a map from H to H tilde. So for omega in H, we have that the omega will be in B. So by the definition of PA, we have that this equation is true because, well, we consider the product by F and we consider its minimal polynomial applied in this guy. So this is 0 in B, but that this is 0 in B means that, well, there exists one form such that this looks like this one. So the Gauss-Manin connection is, well, we consider this eta over this polynomial. This is the definition. And we have we have that this is true, also true, and this is the equation that relate the topological ideas with an algebraic idea. This is like the bridge between these two words, this equation here. And well, in this H tilde, we can consider this subspace, this subset, which is the subset generated by logarithmic forms with pole along Q. And we consider this subset L, which are, well, here we have the sum of logarithmic form, but with the lines in the numerator of F. And here we have the logarithmic form associated with the pole, with the Q over Q. For sure, we have a condition in the coefficients lambda, which are this one. And this condition is in order that this omega define a foliation in P2. Remember that if for omega define a foliation in P2, we have a condition in the integrability, but also we need that when we do the inner product, with the radial vector field, or the contraction with the radial vector field, this will be 0. And this condition ensure that. Well, here we have a proposition with a description of the kernel of the Gauss-Vanning connection. Here this nabla2 means that, well, we compose we apply the Gauss-Vanning connection, again we apply the Gauss-Vanning connection. So if omega is in the kernel, then omega looks like this one. F, our F, times eta 1 plus eta 0, where eta 1 and eta 0 are guys in this set. Moreover, if omega is also in H, not in H tilde, then we have an explicit description of omega. And this is just, well, F times the sum of this logarithmic form associated with the lines in the numerator of F plus dq over q. Well, here we can consider another logarithmic forms in H, but because the only non-reducible fiber is over 0, we separate the fiber over infinity, and we have the fiber over 0 and the fiber over other critical values, but the other fiber are irreducibles. So when we compute the logarithmic form in this case, in the Bristol module, this form will be 0. So only we have to consider these fibers or these logarithmic forms given by the fiber over 0. Also, we have here the condition that ensure that this guy define a foliation in P2. And this proposition is a corollary of another result, which is a description of a closed form for P2. It's maybe a classic result of holomorphic foliation. So by using this, we can prove this explicit description of some guy in the kernel of nabla2. So until here, I talk about holomorphic foliation, but now let me set what is a holomorphic foliation for us in order to define what is the degree of foliation for P2. So the idea is, well, if we want to describe a holomorphic foliation in P2, we consider an open covering of P2 indexed by I. Sorry that I use I for many things, but this I is just an index. Well, we have an open covering here, and we have a collection of holomorphic one forms on UI. And also we have these holomorphic functions, Cij, which are defined in the intersection between these opens, and they have this relation. For sure, this relation define we can prove that these Ci they have cocycle properties, and this Ci will be defined a line bundle L. So at the end, if we want to define a foliation is defined by this alpha on P2, where this alpha is a section of this vector bundle over P2.
Daniel, maybe just for foliations in P2, you don't need this language. I mean, you're putting too much stuff.
Yeah, but just let me say why I want to say that. It's just for the definition of the degree. So, as Jose will say, he said that, okay, also we can define this foliation for a meromorphic one form. And the idea is, okay, we can shoot this guy here, some section in this line bundle different from 0, and we have this definition. Omega is alpha over S in P2. So with this, we have a allomorphic form, allomorphic foliation, but defined by a meromorphic form. And with this, we can define the degree of the foliation. And the idea is, okay, we can consider the divisor of S, the zeros minus the poles. So like the definition of the degree is just this one. The degree of a meromorphic form, which define a foliation, is just the degree of the divisor of F minus 2. And let me give two examples which illustrate this definition. The first one is the foliation with first integral. So alpha in this case will be this guy, which is not meromorphic, it's just this P, Q, and Q are numbers, B and A are polynomial, homogeneous polynomial in C3 with degree A plus 1 and B plus 1 respectively. And P over Q satisfies this condition. So we have that, okay, we can define the same foliation of alpha, we can define with this df, where F is this meromorphic map, A over P and B over Q. So in this case, for example, the section S will be this guy. So we can prove that, or we can show that alpha over F is df. Therefore, the degree of this foliation will be the zeros of S, which is B plus 1 times Q plus 1, minus the poles of this part, which is this one, minus 2. And this is the A plus B, which is a very known fact. And something similar, if we consider, well, this is another example, is the logarithmic foliation. We have this map here, which is not meromorphic, with the condition that I said before, in order to this guy satisfies a allomorphic foliation. So we have that if we consider F of this product here, alpha over F looks like this meromorphic, or well, this meromorphic form. So if we want to compute the degree of this foliation, we compute the divisor, or the degree of the divisor of F, which is this sum minus 2. And these are the degree of the logarithmic foliation and the degree of a foliation with first integral. And this is what I introduced this definition with this section, just in order to be more clear with the computation of the degree of the foliation. Well, this is another ingredient. I think it's the last ingredient that I introduced for proof the main theorem, the main theorem in this work. This is the relative exact one form. This is a very it's a very cases of study, very studied in many articles. It's a study the relative exact one form modulo some foliation. Here we have this study for a particular case that we have that this F, the product of lines over product of lines. So the proposition is this one. We have a omega, a meromorphic one form with pole along D, where remember this Q equals 0. If omega is relative exact modulo this foliation, then omega looks like this one, where G, where G and T are meromorphic functions with pole divisor, well, with pole along D. And remember that, well, an alternative form to define a relative exact form modulo some foliation is that if we consider the integral of omega in any loop in the leaf of this foliation, then this integral is 0. This is the definition of that this guy is relative exact form modulo of this foliation. The idea is if we have this condition that this is 0 over any cycle in the homology of this on the leaf of this foliation, then this omega have this particular form. This is the idea. This is what means this proposition. So now we have we can prove the third main theorem. So we consider a holomorphic foliation defined by one meromorphic from omega with degree d with poles along d equal q equals or q equals 0. So if we have this continuous family of vanishing cycle delta t in the fiber of F, well, and here we have to say that these vanishing cycles which we are considering here are different from this sigma, as I said, which appear because the presence of point of indeterminacy. If we consider another other vanishing cycle, then we have this condition in this family. Then our form, the form which describes this foliation, have this explicit expression: is f, the polynomial, the rational map, times these logarithmic forms which coming from the lines which define the numerator of f, plus the q over q, which are the logarithmic form with pole along q, plus a meromorphic function with poles along d. And well, again, here we have the condition such that this define a foliation. Well, this have degree 2d, as we say. We can compute the sum of the degree here is, because this is our lines, this is d plus 1. This guy have degree d plus 1. This is d plus 1 plus d plus 1 minus 2. It will be 2d, which is the degree of this form, as we said at the beginning. Well, now, because I have a lot of time, I want to say that what is the idea of this proof? The idea is, well, we have, this is the hypothesis, and by using this relation of the Gauss-Bonnet connection, we have that this is equal to this, and this from the hypothesis is 0. So we have that this will be 0, and now by using that the monodromy action on a vanishing cycle different from sigma k generate the homology of the compact fiber, this will be 0 over the compact fiber on cycles in the homology of compact fiber. Now we have to prove that this also is true for cycles around point of indeterminacy. It is possible to prove that. So at the end of the history, we have that this will be 0 for any guy in the homology of the affine fiber. So by using the previous proposition, we have that, okay, this guy looks, this nabla to omega is some guy like this one. Then in this case, we prove that omega, nabla to omega, will be 0 in the Briscoe module. So omega is in the kernel of nabla2. And we have an explicit description of the kernel of nabla2. At the end, we have just this coming from this proposition of the description of nabla2, and in this process also appears some meromorphic function and so on, and we have to prove that the degree of some meromorphic functions will be 0, and these are constant. At the end, we can aggregate all these other polynomials in this just G. So just is that we obtain this part from the description of the kernel of nabla2, and this part is, well, by computing the degree of the meromorphic forms that appears in this process. Well, this is the end. Well, before I finish, I just want to thanks to Jorge Duque, because, well, his discussion at the first part of this article was very, very, very useful for me and was very enlightening for the development of this work. And this is all. Thank you.
Okay, thank you, Daniel. Younes, can you stop recording? I have